So the answer is that this graph is a wrong representation of what we want. And the right way to depict those relationship is here, so that only B and C precede F, and A does not precede F. So you see when we add this dummy node 4 here, and let A to precede D and E in this way, and then B and C precede F this way, then this is the correct way to represent that only B and C precede F. You see, originally we had this way, and then the A will also precede F, but we don't want it. At the same time, we want A to precede E. So we can't take this dotted arrow off. We still need it to represent that A precede E. So what we did is that we add this dummy node 4 here, and let A precede D and E in this way, and let B and C precede F. Did you find the right way yourself? Okay, next let's talk about some general rules, or a summary of the general rules that we used to construct a network diagram. First, the node 1 represents the start of a project. So this node here is the start of project. It's sometimes called the start node, and we may just put a start inside of it. An arc should lead from node 1 to represent each activity that does not have predecessors. Recall in this example here, we have A, B, C, 3 activities that do not have predecessors. So they all start from this start node, connect to their next node. And the final node represents the completion of the project. So this final node here represents the entire project is completed. And sometimes we put a finish inside this node to represent it is the finish node. The node should be numbered so that the node representing the completion of an activity always have a larger number than a node representing the beginning of an activity. So if we number our node, we will have this as node 1, and we will have this as node 2, node 3, node 4. So you see that this node 2 is the completion of an activity A, and it is greater than this 1 here, which represents the starting of activity A. Similarly, node 3 and 4 are larger than this 1 number here, representing the completion of activity B is larger than the beginning of activity B, and the C the same. Here we will have, say, 5, node 5, and here node 6, node 7. And our node 1 is the start node, and node 7 is the finish node. An activity should not be represented by more than one arc in the network. Remember that we said we can use C here because one activity should be represented by just one arc. And also, 2 nodes can be connected by at most one arc. So these 2 nodes, we only connect by this B, because this node here represents the completion of one activity here. And if we have more than one arcs, it does not make sense that we have 2 activities coming to the same node and also starting from the same node. But we can have more than one arcs going to the same node, or we can have more than one arcs, like this ones, coming out from the same node. What we can do is that to have more than one arcs connecting the same pair of node. This is not right. Okay. So now let's look at another example, an assembly project. So a widget is made by assembling one unit of subassembly 1 and one unit of subassembly 2. Before production begins on the subassemblies, raw materials must be purchased and the machinery must be modified. Before the subassemblies can be assembled into the final widget, subassembly 2 must be inspected. So this is a kind of like a typical description of what activities need to be completed to complete this assembly project. And also, it gives the relationship among those different activities. When you plan for a project, usually you would have an understanding of the project, especially if it's a simple project like this. You will know what activities are needed and their sequence to be completed. So the first thing to do is to list the activities and their predecessors in the table, that action table, and we estimate the duration of each activity, and then we can draw a network diagram for this project. So let's look at this first. How do we list the activities and their predecessors in the table? So this widget is made by assembling one unit of subassembly 1 and one unit of subassembly 2. Before production begins on the subassemblies, raw material must be purchased and the machinery must be modified. And before the subassemblies can be assembled into the final widget, subassembly 2 must be inspected. So where does this project start? You see, this is like the final step. So this part is the final step, and before the assembly 2 also need to be inspected. And before the production begins on the sub-assemblies, raw material need to be purchased and the machinery need to be modified. So we can see like this is 1, 2, raw material need to be purchased and the machinery must be modified. It seems like these two are the two activities that need to start first, and they can be done in parallel. And then the production, or need the production of the two sub-assemblies, right? And then sub-assembly 2 need to be inspected before the final assembly. So if we take a look, A, we need to purchase the material. B, we need to modify the machinery. And you see that these two activities do not have predecessors. That's what we said, that these two activities can start in parallel. And then we will need to produce subassembly 1 and produce subassembly 2. So even though here I put only a 3 here, that is actually two activities, subassembly 1 and subassembly 2. So these two need to be done, and before the assemble work can start, the subassembly 2 also need to be inspected. Okay, and in this detailed table, we get to know that produce subassembly 1, we need to purchase material, and to produce subassembly 2 is modify the machinery. So these are the predecessors of those activities, and the duration in days are also given. Now we'll look at this table and convert it into a network. We can just start the draft here. We're going to start that start node first, and then we connect those two, A and B, those two activities that do not have predecessors. And then A is a predecessor of C, so we will have C following A. And we also have B being the predecessor of D. So D will follow B. Then D is the predecessor of E. Both C and E are the predecessors of subassembly 1 and 2. So I'm going to make this longer. F will follow here. And F is the last activity, so we can complete the project. Okay, so you see it's pretty easy to come up with this network. And to put it in a nicer way, this is the network, and also we have the activity durations written after our activity. So the way to write it is the activity name, the A, and the comma, the duration of the activity. Now we can work to find out the critical path of this network. So we studied the activity relationships to determine the precedence orders, and then we develop this network, apply the activity name and the times to the arc. And because we are using activity on arrows, so the activities will be written on the arrows, and those nodes represent events, like the completion of a certain activity or activities. Then we're going to perform a forward pass to establish the earliest start and the earliest finish time for each activity. So what does this mean is that we want to find out when can an activity start the earliest time, or the earliest time that an activity can start, as well as the earliest time that an activity can finish. So we do this in a forward way. We'll talk about what do we mean by forward here later. And also we are going to find out the latest finish and the latest start time for each activity. So what is the latest time to start an activity without delaying the entire project? And also what is the latest time to finish an activity without delaying the project? And we find out these values by going backwards after we are done with the forward path. And then we can compute slack times and determine the critical path. So the slack time is how much time you can have, how much flexibility you have to complete each activity, how much time you can delay a certain activity. And when we go with the forward and backward path, we're going to put some more values on our network. Recall that first we put on the arc the activity name. For example, here the activity name is K here, and it takes T days to complete it. And then we're going to go forward to find out what's the earliest start time for this activity and what is the earliest time to finish this activity. And then we go backward to find out what's the latest time to finish this activity and what is the latest time to start this activity. And for those circles, those nodes that represent the events, we also have their event time. And you can see for each event, we have their late time and early time. Recall that a node here represents the completion of activity K. So this event is saying that what's the latest time of this event happen, or what is the latest time that K can be completed, and what is the earliest time that K can be completed. And because this event here at the beginning represents the beginning of activity K, So this late time and early time here represent what is the latest time to start K and what is the earliest time to start K. If you don't remember it now, it's okay. We're going to use some examples so you will remember this better. So here are some terminologies that I have on the slides, and you can refer to this slide if you don't remember what exactly each of those symbols represents. When we perform the forward pass, here are the steps. So the earliest occurrence time of the initial event is 0. So that is like the start of the project. We give it 0. Then the earliest node occurrence time is the largest of the earliest finish time of the activities merging to the node. If there are more than one activity going into a node, then that node time represents the completion time of all the different activities leading to it. Of course, we have to complete all the activities to claim that event, to claim that all the activities are done. So we choose the latest or the largest finish time for the activities to be that event time. And each activity begins as soon as its predecessor node occurs, so that the earliest finish time equals to the earliest start time plus that activity time, or that event time plus the activity time. Again, we'll illustrate this in our example here. Okay, so back to this example here, we're going to use this table to carry out that forward pass first. So this is our node 1. And our node 1's early start time is 0. So that means the start time of our activity A, the early start time of our activity A is 0. We write the early start and early finish time under the arrow. So if A start at day 0 and it takes 6 days to complete it, then its early finish date is 6. Similarly, for B, its early start time is 0 and it takes 9 days to complete B, so its early finish time is day 9. And we'll continue here, okay? So this node 2. Since there's only one activity, which is A, goes to node 2, then node 2 here represents the completion of activity A. So activity A can be completed by day 6. So that's the early time of this event, which is A being completed. And this 6 will go to here, because when A complete by day 6, C can start. So C's early start time is 6. And the 6 plus this 8 here is 14, representing that by day 14, we can complete C. And if we go down here, this node 3 represents the completion of activity B. And since B can complete by day 9, this event early date is 9. And that 9 will come to here to be the early start time of activity D. And D plus 7 is 16. So we get day 16 will be the early finish date of our activity D. And that also translates to here to be our node 4, the event being D is complete, 16. And that 16 will come here to represent the early start time of activity E, and plus this 4 days gives us that we can complete activity E on day 20. Now this is the one node that has 2 activities merging to it. So what will be the event early date? Now, if we consider what this node represents, it represents the completion of both activity C and E. So if that's the definition of this event, then the earliest date of this event would be 20, which is the maximum among the 20 and the 14, because we can't claim that both events are done if only C is done. We have to make sure both are done, so that is 20. We take the bigger value here. Now this 20 comes to here, which becomes the earliest start time of our activity F. Now the earliest finish time of our activity F is 23. So with this, we finish the forward going. We have our completion event. Node 6 event, early event date is 23. So with this, we can complete our forward going path to find out the earliest start date and the earliest finish date for all of our activities and all the events.
Now this shows the summary of the network we have after we finish the forward path. Next, we're going to go to the steps to backward path. So the latest allowable occurrence time of the single terminal event is taken as the earliest occurrence time calculated during the forward path. What does this mean? This node 6 is our terminal node, which means the last node or the finish node of our project. Its latest time is the same as its earliest time, because the time that a project complete is the earliest and the latest, unless you want to delay it. And the second one, the latest allowable finish time for an activity is its successor node's latest occurrence time. The latest finish time of an activity equals to the latest time for that successor node. And the latest possible activity start time is its latest allowable finish time, subtracting the activity time in question. And that is, the latest starting time of an activity is its latest finish time, subtracting the duration or the time it takes. So if we look at this activity F's latest finish time is 23, because that's what this event here indicates. This event indicates the completion of activity F. And since the latest time is 23, so this 23 comes to here to be the latest finish time of our activity F. And then to calculate the latest starting time of F, we use this 23, subtract this 3 here, because if we have to finish activity F by day 23, and it takes 3 days to complete F, then we have to start F by day 20. This is what it meant here. Then the latest allowable node occurrence time is the smallest of the latest allowable start time of the activities emanating from the node. So when we go backward, that has some activities that follows it. Okay, suppose this is, we are looking at this node here, and we have the early start, early finish, late finish, and late start. Say these are the ones, okay. And then we have another activity here, the twos. we've already have this one. That's the early event time. Now, how do we determine this late time? This late time here. How do we determine this one? If we have more than one activity coming out of this node, this late event time will take the smallest one among the activities that coming out of it, those late start time. And if you think about it, the reason is that if the latest start time, say this one is 5, okay? And if the latest start time for this event is 3, then we have to take this 3 instead of 5. Otherwise, this activity here will be delayed because the latest date for it to start is day 3. So we have to take the smaller value instead of this bigger value. Otherwise, this activity will be delayed because this event not only represents the completion of the activity before it, it also represents the starting of the activities after it. So this late time represents the late start time for all the activities emanating from it. So we need to take the smaller number. Let's use our example to illustrate this further. So now we are going backward. This terminal node, which is the completion of our project, is going to have the same late time as the early time. And then this late time comes here to represent the latest time for F to complete is by day 23. 23 subtracting 3 gives us 20. And that is the latest start time of activity F. And then this 20 comes here, representing that the late event time for node 5 is also 20 because this node represents the starting of activity F. So if F's latest starting time is 20 here, then this event's latest time should be 20. Okay, then this 20 would go to here, or have the latest finish time for our activity C and our activity E, because this event also represents the completion of activity C and E. So if its late time is 20, then the latest date to complete activity C and E are both day 20. Now we look at the C first. It takes 8 days to complete C, and C has to be done by 20, the latest. Then the latest start time for activity C will be 12, which is 20 subtract 8. And for E, we use 20 to subtract 4, we get 16 here. Okay, then we'll continue. So this 12 will go to here to represent the late event date of our node 2, and our latest finish date for activity A will be 12. 12 subtract 6 give us 6. And down here, 16 becomes here, and the latest finish date of activity D is also 16. 16 subtract 7 gives us 9. And since we only have one activity here, 9 goes to the event's late time for node 3, which continue to go here. 9 subtract 9, 0. So now when we come to this node, what number should we put here? That relates to what we just talked about. We have 2 activities coming out of this node. And what is the latest date of this node? We need to take the smaller value, which is 0. Because this node represents the starting of both activities A and B. Even though you can start A by day 6, the latest, you can only start activity B by day 1. That's the latest. So 0. And that means if we start this event at 6, by day 6, we're going to be late for 6 days for activity B. So we have to take this small value, which is 0 here. Okay, so this slide gives you a nice summary of what we just worked on, the backward path. We started from this number coming here and this number coming here. Then we calculate this number, and this number went here and here, here, and so on.
Next, once we finish the complete network calculation, we can find out the slack times. The slack of an activity is the amount of time or the amount of flexibility an activity has that you can delay it without delaying the entire project. And it is identified by taking the difference between the late finish time and the early finish time. So you can use the late finish time, subtract its early finish time, or you can use the late start time, subtract the early start time. And if there's a difference between them, then that means there's a slack for this activity. Using this as an example, if we look at activity A's earliest finish time is day 6, and the latest finish time is day 12. That means the earliest time you can start activity A. That means the earliest time you can finish activity A is day 6, but you can also finish it by day 12. There's this 6 days slack, which is the difference between the 12 here and the 6 here, for A that you can delay without delaying this entire project. So for A, its duration is 6, but the slack is also 6. And if we look at activity C, C's earliest finish time is day 14, and the latest finish time is day 20. So this 20 subtracting this 14 here is a 6. So C has a slack of 6 days. The maximum amount of time that you can delay C is 6 days without delaying this entire project. And if you look at activity F, the earliest finish time and the latest finish time are the same. Same for activity E, they are the same. And if you look at the starting date, they are the same. And for activity D and B, those are the same. So the only 2 activities that have non-zero slack are activity A and activity C, which we can see from the difference here, or you can use the starting time. So the 12 subtract the 6, or the 6 subtract 0, they are 6. So that means if we choose to delay A, or if we choose to delay C, they can be delayed for 6 days. And note here, this slack is assuming that all the other activities on this path will not be delayed. Say if we delay A for 6 days, then C will only have a slack of 0 because we used up that 6 days. And if we delay C for 6 days, then A will have a slack of 0 because that 6 days are used up here. Or we can delay A for 3 days, C for 3 days. As long as the entire slack is 6, then we are good.
And when we find activities that do not have any slack, which means their early time equals to their late time, or their early finish time equals to late finish time for the activities, then we find those critical activities that cannot be delayed. And if a path that connecting those activities on which all the activities cannot be delayed, then we will find that's a critical path. Critical path is found after we complete the forward and the backward path.
And the path is called a critical path because if you delay any activities on that path, you will cause the entire project to be delayed. So now use this example again. What is the critical path? The critical path is the one that has 0 slack. So we identify that the B has 0 slack, and goes to D that has 0 slack, goes to E that has 0 slack, and then goes to F has 0 slack. So this is the critical path of this entire project that contains B, D, E, and F. All of those activities on this critical path cannot be delayed, otherwise the entire project will be delayed. Now let's wrap up this project. So we find the slack by looking at the late finish time and the early finish time's difference. As we mentioned, you can also use the late start time subtracting the early starting time. As long as they are consistent, if you use the finish time, then use the finish time here. If you use the starting time, then use the starting time. Then we also find the critical path, which is B, D, E, F. And the length of this critical path is 23 days, which is the length of our entire project.